Okay, there we go. Now, let's multiply that all out, but let's do it in parts first. I'm going to take the negative 2.95 and divide by the 2 times 4.9, which is 9.8. So we'll divide that, and we'll get a negative 0.301 seconds. Then I'm going to take the plus minus, evaluate this, keeping in mind we've got a negative there, makes it positive. Evaluate the square root, divide by that, so we'll have plus or minus that term, which is 1.80 seconds. We evaluate that, plus or minus, and what do we get? We get negative 2.10 seconds, or 1.50 seconds. Okay, now what answer do we want? Well, we want the positive answer, the 1.50 seconds. So there's the time that we want. But before we move on, let's think about this just for a second. Why are we getting two answers, one negative, one positive? Well, let's think about what we've talked about before. Let's think about this motion. The positive answer is the time that it takes for this point, the object, to make it down to the ground. If we could trace this path back in time, imagine this ball was continuing this path backwards in time, it would look something like this. The equations that we're looking at are asking for the time when the final y position will be 0. Well, if we could imagine this coming backwards in time, it would actually be 0 at some point in the past back here, some negative time. Notice that the time in the past would actually be a larger negative time than this one because the ball is still, it's going down here. It has to go up first and then back down. So the negative time will actually be a little bit larger in magnitude than the positive time. And that's what we see, negative 2.1 versus positive 1.5. Coming back a step, what do these mean? What is this negative 0.301 plus or minus that amount? Remember from other problems, the negative 0.301, that's the time to get back to the peak here. That is the time earlier. So the peak is actually earlier than where we are in the problem. And then plus or minus 1.8, so negative 1.8 more seconds brings us to this point. 1.8 seconds after this one brings us to that point. So that's the symmetric time from the peak of the motion that we could go either earlier or later to find us at two symmetric points where y equals 0. Okay, well, that's a good explanation as to what those times really mean. What we're looking for, though, is the value of 1.50 seconds. So that's actually the answer to part A. How much time does the ball spend in the air? 1.50 seconds. So what we want now is the final velocity. We need to find Vy. So let's see if we can solve for Vy. All right, I hope you all have this. I'm going to erase this part. Now let's solve equation number 4 and solve for Vy. We've got Vy squared equals V naught y squared plus 2ay, y minus y naught. Again, we have y is equal to 0, so we've got 0 there. We've got Vy squared is equal to V naught y squared. V naught y is negative 2.95 meters per second. We're going to square that, so that's going to make it positive. Then plus 2 times ay, which is negative 9.80 meters per second squared, times negative y naught, and y naught is 15.5 meters. So notice again, we've got a negative times a negative, that makes it positive. So we've got a positive number plus a positive number. Combine those, and then Vy will be the square root of that. And remember, square roots can always be positive or negative. So when we evaluate that, we get plus or minus 17.7 meters per second. Now, which one do we want? What is Vy? Well, keep in mind, over here, it's coming down. So the value that we actually want in this case is the negative. We want the negative velocity because we know it's on its way down. What does the positive velocity mean? Well, again, this equation is basically looking for a solution where our final y is 0, but the y value is 0, but the y value is also 0 over here, where the ball could have been going up with a positive y component of 17.7 meters per second. So again, even though it's not the component that we're looking for this particular problem, it does have a physical meaning, and we can see that it's the same point where we had the negative time, we would have had a positive velocity. Okay, so what is Vy in this case? Negative 17.7 meters per second. So what is our final velocity? Well, we have an x component that is 11.0 meters per second, and that's positive. So here is x, 11.0 meters per second. We have a y component that's negative, so down at 17.7 meters per second. I'm not going to put the negative sign in there because I drew it downward, which is what we know because it's negative. So let's see if we can't figure out now what is our final velocity magnitude. Well, we'll find that from Pythagoras. We know that v squared is going to be this squared plus that squared, or v equals 11.0 meters per second squared plus 17.7 meters per second squared root. Multiply that out, excuse me, and we find v is equal to 20.8 meters per second. Let's find the angle. Here we go. Let's look for that. We know tan theta is equal to opposite over adjacent, or 17.7 meters per second over 11.0 meters per second. Divide that out, take the inverse tan, and we find theta is equal to 58.1 degrees. Let's just think about that just for a second. We know this opposite side is larger than this one, so we expect this angle to be what? Well, whatever it is, we expect it to be larger than 45 degrees. Is that what we found? Yeah. So at least that seems like a reasonable result. So what is the final velocity? We can say v is 20.8 meters per second at 58.1 degrees, and this will be down from the x-axis, or below the horizontal. There we go. Excellent. And there is our final result for that problem. Very, very good. Okay, now I want to take a little side trip just for a second. I want to talk about one slightly different thing than these two-dimensional kinematics problems. Because this is typically the place where this topic is put in, and you might see this if you have to take one of those standardized exams that has a physics component, maybe the MCAT or something like that. So if you ever have to take something where you might have to do this, I want you to have seen it before. All right. This is actually a combination of velocities in different directions, and this is called relative velocity. Relative velocities. Okay, let's imagine that we start out with a simple problem. Let's imagine we've got a train or something like that, and let's imagine this train is going down the tracks at, let's say, 20 meters per second. 20 meters per second. And let's imagine that inside the train car there is a person who is walking, and let's say they're walking in the train relative to the train, let's say maybe 5 meters per second. And then there's a person here standing on the ground who is looking at the person in the train. The question is, how fast does the person on the ground see the person in the train moving? Now remember, the train is moving at 20 meters per second. The person in the train is moving at 5 meters per second relative to the train. So in 1 second, let's say the train will move 20 meters down the track. The person will move an additional 5 meters further away as they walk in the train car. So this person will actually have moved a total of 25 meters in 1 second. So how fast are they moving? 25 meters. Well, how could we have gotten that a little bit easier? Obviously 20 plus 5 gives us the total velocity of the person, 25 meters per second. Well, we're going to do the same sort of thing, but even in 2 dimensions, or 3 dimensions. We can actually take these velocities and write them as 2 or 3-dimensional velocities. Let me make some definitions first. I want to say that I'm going to call the person in the train, I'm going to call this person A. The train I'm going to call B, and the person on the ground I'm going to call C. Now, VAB I'm going to write as the velocity of A relative to B, or measured by B, you might say. So this is the velocity of A measured by or with respect to, so I'll write WRT, with respect to B. And then VBC will be the same thing. So this will be the velocity of B with respect to C. And then finally VAC, this will be the velocity of A with respect to C. Okay? Now, what is the velocity of A with respect to B? So A with respect to B, the velocity of A relative to the train. Well, we know that is 5 meters per second. What is the velocity of B, the train, with respect to C, the person on the ground? How fast is the train moving with respect to the person on the ground? Well, that's 20 meters per second. And what is the velocity of A, the person in the train, with respect to the C, person on the ground? Well, we said that was 25 meters per second. So what we see is that VAC is equal to VAB plus VBC. And this result, while it's true with just simple values going in the same direction, is actually going to be a correct vector equation. So I'm just going to stick vector signs on there, and it's going to work just as well. So let's take a look at something like this in 2 dimensions. Let's keep in mind, any of these values, it's the velocity of the first subscript with respect to, or as measured by, the second subscript. Let me write this back up here. VAC is equal to VAB plus VBC. Okay? Now, let's imagine that we've got a river, for example. So here's a river. We're looking at it from above, and here's the water in the river. Here's the water. And the water in the river, let's say, is flowing that way at 15 meters per second. We have a boat. Let's say here's a little boat that is moving across the water at, let's say, 5 meters per second. So the boat is going directly across the water, but the water is going downstream. So what's the boat going to do? The boat is going to end up going, say, in that kind of direction. The boat is going to end up going downstream as it moves across the river. What exactly is this velocity? Well, let's think about this. We will call the boat A, the river B, and the ground C. So A is the boat, B is the river, and C is the ground. So, what is VAC? VAC, that is the velocity of the boat relative to the ground. So that's what we're looking for. How is this boat moving relative to the ground? Well, what is VAC? VAB. VAB, That is the velocity of A, the velocity of the boat, measured by the river. Well, the boat is moving directly across the river. Well, let's draw some coordinates here. Let's say x is downstream and y is across the river. So VAB is going to be what? It is moving across the river in the y direction, so VAB will be 5 meters per second in the y-hat direction, across the river. What is VBC? VBC, that's going to be the velocity of the B river relative to C, the ground. How is the river moving relative to the ground? Well, the river is flowing downstream in the x direction at 15 meters per second. So VBC will be 15 meters per second in the x-hat direction. So what is VAC? VAC is VAB plus VBC. It's going to be the sum of these two. So it's going to be 15 meters per second x-hat plus 5 meters per second y-hat. We just add the two smaller, you might say, parts of the velocity. The part of A relative to B, the part of B relative to C, and that gives us A relative to C. Well, let's combine these. What do we have? We've got a vector that is 15 meters per second in the x direction and 5 meters per second in the y direction. What is the final velocity? Well, we can use Pythagoras to figure out the magnitude. We know that V will be equal to 15 meters per second squared plus 5 meters per second squared root. Evaluate that and we find that V is equal to 15.8 meters per second. We can find the direction with tan theta is opposite over adjacent, or 5 meters per second over 15 meters per second. Divide that, take the inverse tan, and we find theta is equal to 18.4 degrees. So what is our final velocity? It is 15.8 meters per second at, excuse me. So we end up with the final velocity of 15.8 meters per second at an angle of 18.4 degrees, and we might say this is from the bank or from the shore or something like that, or maybe above the x-axis, to use our nomenclature that we use for all the others. Okay, so there we go. There's our final velocity. So the whole idea about relative velocities is this equation here. If you've got something moving relative to one thing and then something moving relative to that, the final velocity is just essentially the sum of the two measured velocities. The velocity of A measured by B plus the velocity of B measured by C is then equal to the velocity of A measured by C. That's the bottom line for relative velocities. Okay, so back to some more two-dimensional kinematics problems.